Welcome to this next lecture on compact operators. So we have seen before in one of our previous lectures, or web notes, an introduction to linear operators between two normal vector spaces, and if they are continuous. In fact, they are continuous if and only if they are bounded. So we introduced the concept of let me just consider here, let throughout, okay, x and y be two non-vector spaces. So we defined L of xy to be linear operators between x and y, and B x y to be the continuous linear operators or bounded linear operators, okay? And now we have a new definition. T, which belongs to L of xy, is said to be compact if and only if for any bounded subset A of x, T x bar, the closure, is compact in Y. So in other words, it's relatively compact, and the image of a bounded sense is relatively compact in Y. Okay, so note, it's very easy to see that if T is compact, then the image of E1, the unit ball, closed unit ball, closure is compact in Y. So in particular, it is bounded. So T of B1 is bounded in Y, which implies that T is bounded. In other words, T is continuous. So compact operators are continuous. Okay, so let's put this as a basic result. Okay, theorem. Okay, if T belongs to L of xy, okay, and T is compact, then T is bounded. So compact operators are continuous bounded operators. If we use a sequential characterization, so here's sequential characterization. So if we use the sequential characterization of compactness, because we're in metric spaces, we get the following result, theorem. Let T belongs to L of xy. So of course throughout we assume that x and y are normal vector spaces. T is compact if and only if for any bounded sequence in X, then sequence xn, xn in X, okay, the sequence T of xn, the image in other words, okay, has convergent subsequence in Y. Okay. Let us give an example of a compact operator. Example. Let x be the continuous functions on 0, 1 with the subnorm. This is a Banach space that we have seen before. And let k defined with two variables. Okay, so xy is k of xy, and we assume that it is continuous. Okay, we know that the product 0, 1 cross 0, 1 is compact, and therefore we have a continuous function on a compact set. And the square is just the square. So define t from x into x by t of f at x is the integral from 0 to 1 k of x y f of y dy. Okay, so k is called the kernel of this product integral product defined map. It's very simple to see that t in fact is in L of x. So it's a linear operator defined on x. These are just properties of the integral. And we have for any f in x, so it's continuous function 0, 1, therefore it's bounded. So we get absolute value of tf at x. This is less or 0 to 1 absolute value of k of xy, absolute value of f of y dy. And then of course we have this one here, which is less than the sup, which you can put it outside. So this is less than the sup of f of x, the integral from 0 to 1 absolute value k of xy dy. In other words, this is the norm of f, and we have the k of xy absolute value dy. So that shows us what that t is bounded as an operator. In other words, t is continuous, so it belongs to v of x. Okay? Let us now show that in fact claim t is compact. And in this case, if t is compact, okay, just we wanted to show that it's very easy to prove that t is bounded, but if we prove that t is compact, then there was no need for that. Okay? So let S be a subset of X which is bounded, non-empty, and bounded. So this is a set of functions defined on 0, 1, continuous functions 0, 1, which are uniformly bounded. Set is bounded of these functions. We want to show that. Let us prove that T of S is relatively compact. Relatively compact. So this should remind you of the Ascoli-Arzela theorem, because that's exactly what it is. So for this reason, we need to show that T of S is equicontinuous, okay? And if you take the image of every point, since S is bounded, then if you take any x, Ts of x is bounded in R, and therefore it's going to be relatively compact. Therefore, the family of functions will be relatively compact. That's Ascoli-Arzela theorem. So we are going to use it right now. So first, let us prove that Ts is equicontinuous. So first, let us prove that Ts is equicontinuous. So this is equicontinuity is like similar to uniform continuity for a function, meaning that whatever epsilon, the delta is independent of the element in S. Okay, so let's prove it. So let epsilon be positive. Since K is continuous on a compact metric space, then K is uniformly continuous. Okay, and therefore there exists delta. So there exists delta positive such that for every x1, x2 in 0, 1, absolute value x1 minus x2 less than delta will imply K of x2y minus K of x1y is less than epsilon. In fact, what's going to happen is that in the proof, we'll see it because, okay, let's keep it for the time being in epsilon, but you see that we may have to adjust a little epsilon so we can get at the end epsilon, but that's fine. Remember, we are not talking about 0, 1 being continuous. We are talking about 0, 1 cross 0, 1 in the product. And you can take any distance on it. And therefore there, you cannot take x1 and x2 in this compact set. You're going to take x1y and x2y, and the distance between them depends on x1 and x2 because it's the same one. Okay? So anyway, so here, this tells us what? That T for any f for any f in S, Tf at x1 minus Tf at x2. Okay, so this is equal to the integral absolute value from 0 to 1 K of x1y minus K of x2y f of y dy absolute value, which is less or equal than the norm. We have done this before. Integral absolute value K of xy minus K2 y dy. So since the function inside the integral is always less than epsilon, then this will be less than the norm of f times epsilon, okay, which is less than the sup of the norms of f in S times epsilon. So you see this number here exists because we're assuming that S is bounded. Okay, so in fact, when you go back here, if you want to have epsilon at the end, you just have to divide this epsilon by the norm of the S. Okay, we're assuming that if that soup is equal to 0, I mean, you can even, for example, add 1 just to avoid the fact that this s may be reduced to only one function, which is the 0 function, okay? So here you can say this is less than 1 plus soup of norm of f, or f belongs to s, time epsilon, and this will give us the equicontinuity that we are looking for. So the family T of S is indeed equicontinuous. Okay, so as I said, for any x in 0, 1, if you look at the family or the set T of f at x, f belongs to S, this set is bounded in R, so it is relatively compact. So now Ascoli-Arzela theorem implies T of S implies that it's relatively compact, and this is exactly what we want. So you have an example, a beautiful example of a compact linear operator. Another one, which is really trivial, another example, very simple. Okay, let X be a normal space, any normal space. Okay, and if you take let X star belongs to the dual space, which is the linear operators X from X to R, okay, then X star is in fact compact. And why? Because we're using the properties of R, that if you start with a bounded set in X, the image will be bounded in R, and any bounded set in R is relatively compact. Okay, so it's a property of R basically. Okay, it's also true in any finite dimensional space. So here, this result can extend easily to the following. Okay, so extension of this result, theorem. Let X and Y be two normed vector spaces. Assume Y is finite dimensional. So this is like Rn. Then any T in L of xy is compact. So you see, this extends this example, okay, because R is one-dimensional. But if you take any dimensional subspace, any dimensional normed vector space, you get linear operators are in fact compact operators, okay? And the same comment as we said in the case of the dual space are here, so it's the same. A little property here, okay. Compact operators. Enjoy some nice properties. And the first one has to do with this theorem, okay? The one that we just did. Why? Because people may think that for compact operators, the range is always a finite dimensional vector space. We know that the range is a subspace of Y, but somebody will always think that, oh, the range is always a finite dimensional space. And this is wrong, okay? First, this is not true, because if you take the zero linear operator, okay, take the 0, 1, that assigns for every vector in X, it assigns no, this is not true. My claim is not true. I mean, it's not true that the range will be no, sorry, the 0, 1 will not be a good example because the range is the 0 vector which has a dimension 0. No, the example is the first one we started with, the one with the kernel k of xy. So the image, the range is not a finite dimensional vector space. Okay? So if it's not a finite dimensional space, what can we say about the range? Okay, so here it's about the range. So some of the properties of the range are, number one, theorem. Let T belongs to L of xy. Assume T is compact. Okay. Then the range of T equals T of x is separable. Okay. That's property number one. Okay, proof. We have R of T, the range, is equal to the union of T Bn, where Bn is just the closed ball centered at 0 with the reduced n. So this is x in x, such that the norm of x is less or equal than n for n equals 1, 2, etc. Okay? So obviously T for any n, T of Bn is relatively compact. And we have seen that in metric spaces, compact metric spaces are separable. So T of Bn is separable. Since you are taking countable union of separable set, so R of T is separable. Okay? Next, we have another property, which is very interesting because, as we said, we are not finite dimensional. The range may not be finite dimensional, but what we're going to see next is that it's not far from being finite. We can approximate it by a finite dimensional space. So let us start with some basics. Let x and y be two normal vector spaces. Let T be a linear operator from x to y, which is compact. I'm assuming that T is compact operator. So we know that T of B1, which is the closed unit ball of x, is relatively compact. In y. Okay? And therefore it is totally bounded, which means that for any epsilon positive, there exists x1 xn in x such that t of b1 is included in the union of the balls t of xi epsilon I from 1 to n. So this is just the total boundedness of B1. So now let Y1 to be the span of T of x1, T of x2, T of xn. So this is a finite dimensional space, okay? And let x be in x. So we know that we assume that x is not equal to 0, okay? You will see at the end that the inequality we are going to achieve is obviously valid also for x equal to 0. So let us start with an x which is not equal to 0. Then x divided by norm of x belongs to B1. In particular, there exists an I from 1 to n, 1 I0, such that t of x over norm of x, okay, belongs to one of these balls, okay, meaning that t of xi0 in norm will be less than epsilon, okay? So this implies that, so the norm of t of x, using the linearity of course, norm of x xi0 is less than epsilon norm of x, okay? And so what does that mean? This means that for any x in x, there exists a y in y1, so this is the vector, this is the vector, this is your y, such that the norm of tx minus y is less than or equal epsilon norm of x. Why did they put or equal? Because we can take x equals 0 now, huh? So we can take y equals 0 and you get then 0 less than 0. So that's why here we say for every x in x, okay? So we are now catching the 0. So this tells us the distance from tx to capital Y1, which is the minimum of the norm of t of x minus z in capital Y1, so just the distance to the, this is less or equal than epsilon norm of x. So here, that is exactly what we meant by the range is approximated by a finite dimensional space up to, so here we have a theorem which gives us property number 2 for the range. So here, let x, y, and t as before. So we are assuming that x and y are non-relative spaces, and t is the linear operator which is compact. Okay. Then for any epsilon, then for any epsilon positive, there exists y epsilon a finite dimensional subspace of y, such that for any x in x, the distance between tx and capital Y epsilon is less than epsilon norm of x. So that's property number 2. So here, one more. Okay, so one more property here. In the case when x is reflexive, we have the following. So when x is reflexive, okay, we have the following results. Okay, so we have theorem. Let x, y, and t as before, meaning that x and y are non-vector spaces and t is a compact operator. Assume x let me just make a little correction here, sorry. And t belongs to L of x, y, because we're going to give a characterization. Assume x is reflexive, then t is compact if and only if for any sequence xn weakly convergent in y, in x, then its image is strongly convergent. Is strongly convergent. Okay. Proof. Okay. So let t belongs to L of xy and assume that the image of weakly convergent or strongly convergent, the image of weakly convergent sequences are is the image is is strongly convergent. So the image of a weakly convergent is strongly convergent. So now let us prove that T is compact. Okay, let D be a non-empty subset of X, which is bounded. Okay, we want to prove, let us prove that T of D is relatively compact. So the idea here, either we go back to the definition, which is what I'm trying to do here, or we can also use the sequential characterization of compact operators. We have a choice, and in fact it's exactly the same. That's why I didn't even give you the proof initially. So it is enough, I mean that's why here it is enough to prove that any sequence yn in TD, yn has a convergent subsequence. So basically, I'm gonna boil down to use the sequential characterization anyway. Okay? So the reason is because the assumption itself is sequential in nature. The image of any weakly convergent sequence is convergent, and that's why I'm trying to go back to sequences. Okay? So we know that there exists xn sequence in D such that T of xn is equal to yn. Okay? And now we use the fact that what? D is bounded. D is bounded, so xn is bounded. So this sequence xn is bounded, x is reflexive, okay? Then there exists a subsequence x phi of n, which converges weakly. So now our assumption comes in. Our assumption implies that T of x phi of n is strongly convergent in Y. Meaning, so Y phi of n is strongly convergent in Y. And that's what we wanted. So we start with Yn, which is any sequence in D, and we found that there is a subsequence of that sequence which is convergent. Therefore, T of D is, so T of D is relatively compact. Okay, in other words, T is compact. Now assume converse. Okay, let us prove the converse. Because we said that if and only if, let's prove the converse. Assume T is compact. Okay? Let Xn be weakly convergent in X. Let us prove T of Xn is strongly convergent in Y. Okay? So let us pay attention a little bit here. I'm going to make a little mark afterward to this proof. So let us pay a little bit more attention to this proof. Okay? So what happened? Let omega be the weak limit of Xn. So we know that, okay, let Y star belongs to the dual of Y star. And look at now, we know, okay, that Y star composed with T, okay, of Xn. Okay. Is convergent. In fact, T, indeed, because we have Xn indeed, Xn, okay, T is continuous, okay, sorry, T is compact, so T is continuous. In other words, T belongs to B of xy. Okay? So Y star composed with T belongs to the dual space, right? Because Y star this is the y star composed with t. It takes us from x to y, t, and then from y to r. So this is really a linear function from x to r. And because it's a composition of two continuous linear operators, therefore it is continuous. So we have a continuous linear function on x, therefore it belongs to the dual. Okay? And since it is the sequence xn is weakly convergent to omega, then y star composed with t of xn converges in R to y star composed with t of omega. Okay, so here, what is the main ingredient? This is the remark I wanted to make. What is the main ingredient here? The main ingredient is not compactness. Sorry, it's compact. The main ingredient is the fact that t is continuous. So what we just showed, in fact, that if a sequence is weakly convergent, then the image by t is weakly convergent. If t is continuous. So of course, when we are compact, we are continuous and bounded, but this is the argument that we are using. We don't need compactness for this part, okay? We just need to know that the image of a weakly convergent sequence is weakly convergent in the target space, okay? In the range. Okay, so now this tells me that so the sequence t of xn is weakly convergent in y, right? To t of omega. Okay, so if t of xn is weakly convergent to t of omega, and now we use the fact, now we're going to use the fact that what? That t is compact, okay? So if you take, we know that t of xn will have a strongly convergent subsequence, and this subsequence, if it is strongly convergent in y, so it has to be also weakly convergent. And we know that the weak limit of that subsequence is the same as the strong limit. And since it is a subsequence of t of xn, and t of xn is weakly convergent to t of omega, so the subsequence will have to converge to t omega. In fact, what we have is that any subsequence convergent, any strongly convergent subsequence of t of xn will converge to t of omega. So there is a subsequence converge to t of omega, and any subsequence will have to converge. If it converges, it has to converge to t omega. It means that t omega is the only strong cluster point of the sequence. This implies, using a little bit of metric spaces, that t of xn converges strongly to t of omega. So again, keep in mind, it's very important, just the last part where we use the compactness. So if t is continuous, the image of a weakly convergent sequence is weakly convergent. And the fact that t is compact allowed us to say that the image of this weakly convergent, now the convergent, the weak convergence we have in y, in the images, now becomes the strong convergence because t is compact. And in fact, we can weaken a little bit the definition of compactness to define what we call weakly compact operators, but we'll see. I may do something about this. But otherwise, let's stick to compact because this is a very important part of operators, very important class of operators. Okay, next we summarize, we put in some properties, more properties of compact operators. Okay, but before that, let us just, because I will keep saying compact, let X, Y be two normal vector spaces. Okay. Okay. Let us introduce the notation. Let us introduce the notation K of xy to be T belongs to L of xy such that T is compact. In fact, some other notation for this is the bounded linear operators which are compact between x and y. I have seen this as well. Okay, I don't like it because it's confusing with the balls. And students, if they see for the first time, they may be a little bit. So I will keep k of xy. It doesn't matter as long as we know that what we're talking about are the compact linear operators from x into y. So number one, theorem. Okay. Okay, so here let x and y be two normed vector spaces. Assume y is a Banach space. So sometimes we may need this, sometimes we don't need this. So it's not like we need y to be Banach to have all the properties. Some properties may not need the completeness of y, some of them may. Number one. So K of xy is a closed subspace of B of xy. So for example, to be a subspace, we don't need Banach, but closed, that's a different story. Two, if A belongs to B of xy and B belongs to bounded operators from y to z, where z is a normed vector space, then B composed with A belongs to K of x to z, okay, provided either A or B is compact. So as you can see here, for the property number 2, that we don't need y to be a Banach space. Okay, so mostly we need it to show that it's a closed subspace of Bxy. Okay, proof. Let us show that number 1, proof of 1. Let us prove 1. Okay. I'm not gonna give the proof. Really straightforward that it is easy, and this is a property of convergent sequences. It is easy to see. We're going to use, of course, sequential characterization, that K of xy is a linear subspace of L of xy. So being a linear subspace, we just use the properties of sequential characterization of compactness and the properties of sequences, convergent sequences. Okay, so this will give it. Okay, let us prove now that K of xy is closed. Okay, let A belong to K of xy bar. So the closure of K of xy in B of xy. Okay. Let an in K of xy such that limit of an is equal to A in B of xy. So we're talking about the norm used in B of xy. So the ANs are all compact operators. Okay. And now we want to prove that. Let us prove that A is compact. Okay? Let epsilon be positive. We know that there exists an n greater than 1 such that for every n greater than n, the norm of A minus an minus A is going to be less than epsilon. This is the operator norm, of course. Okay? Now, fix n. That n, the one that we just found. Okay? We know that A n of the unit ball of X is relatively compact. Okay? Then an of B1 is totally bounded. Okay? So there exists x1, xk, and B1 such that an of B1 is in the union of the balls centered in an of xi epsilon. Okay? So now let X belongs to B1. Okay? Then we have, since we have the norm, since the norm of A of X minus A sub n of X is less or equal than the norm of A minus an, norm of X, which is less than epsilon. So AB1 is in the union of the balls AN of X, epsilon X belongs to B1. So now we use the properties that we have seen before in one of the previous lectures. It's a very simple exercise by triangle inequality. So A of B1 is going to be in the union of AN xi's to epsilon I between 1 and k. Okay? And again, okay, so here, using the fact that AN of xi is close to A of xi is up to epsilon, which implies that A of B1 is included in the A of xi's 3 epsilon A between 1 and k. Okay? Triangle inequality. So of course here, I kept it as 3 epsilon, but we could have started from the beginning. Instead of having epsilon, I could have taken epsilon over what? 3. So this way, we'll end up here having to simplify it to epsilon, not to 3 epsilon. Doesn't make a difference anyway. So A of B1 is totally bounded. Okay, so if it is totally bounded, we would like now to claim that it's relatively compact, and this is where we use the fact that Y is a Banach space. So since this is the point, Y is a Banach space, this is the only step, then A of B1 bar is complete. See? So we are totally bounded and complete, therefore we are compact, okay? So A of B1 bar is compact. So for the rest we don't need in Y. So we don't need the completeness of Y, okay? Proof of 2. So the composition of two linear operators, okay? Introducing the subspace Z is just to make sure that the definition, the composition is well defined. So what it tells you is that if one of the two operators is compact, the composition is compact, okay? It's really not really that hard because we know that the image, okay, if the first one is compact, then the composition is compact because by a continuous map, the image of a compact set is compact. So here, this is just let us assume that let A first belongs to K of xy, okay, and B belongs to B of xy. I'm sorry, yz, where Z is just a normal vector space. Okay? Then, we're going to use the sequential characterization of compactness. If xn is a bounded sequence in X, now we use the fact that A is compact, there exists X phi of n, a subsequence of xn, such that A of x phi of n is convergent in Y. And now since B is continuous, since B is linear operators, then B of A of x phi of n is convergent in Z. So you see, this tells us what? That so B composed with A at x phi of n, okay, is convergent in Z. So what we showed is that the image of any sequence, bounded sequence in X, has a convergent subsequence in Z by B composed with A. So B composed with A is compact from X into Z. Okay. Next, assume that. Assume A belongs to B of xy, so it's a bounded linear operator, and B is compact from Y into Z. Okay? So we know that let D be a bounded non-empty subset of X, then A of D is a bounded subset of Y. Since B is compact, then B of A of D is relatively compact in Z. Okay? In other words, B composed with A of D is compact. So the image of a bounded set from X by the composed map B composed with A is compact, therefore the composition is compact. So B composed with A belongs to K from X to Z. Okay? So as you can see here, a remark. Okay. If we assume that X is equal to Y equals to Z, then in this case, what does it mean? We have K of X, we have B of X, and L of X. So we have linear operators from X into X, bounded linear operators from X into X, and compact operators from X into X. What it tells you is that, this is just from algebra, I'm borrowing this from algebra, that K of X is what we call an ideal left, and right, which is very interesting, ideal in B of X. So in other words, if you multiply, being here the composition, any element from K of X with an element from B of X, it doesn't matter whether you multiply from the left or from the right, or you compose from the left or from the right, you stay in K of X, okay? Just a little bit of definition from algebra. Okay, the next discussion is really interesting. So, and what what's interesting is that, let me just set the stage, okay? So this is Reed's work. Okay, so from now on, so we're going to look at a beautiful work of Reed's. So here, let A be an operator, linear operator on the same space, and let lambda be a real number or complex number, doesn't matter. And we consider the operator A lambda equals lambda I minus A. So here I can only consider this operator because I'm talking about the identity map from X into X. So that's why I'm assuming that the target space Y is the same as X. So this operator is obviously what? Linear. So A lambda belongs to L of X. Okay? And in case if A is bounded, then A lambda is also bounded because X is a bounded linear operator. Okay? So if you look at now the null space, okay, is what we knew as, so what's the null space? Null space of A lambda is the set of X for which in X such that A lambda of X is equal to 0. And it's not very hard to see that in fact this is just X in X such that A of X is equal to lambda X. So this is, if this is not reduced to 0, then lambda is what's known as the eigenvalue, an eigenvalue of A, and X is an eigenvector of A associated to lambda, or the eigenspace. Okay, so if you took a baby matrix algebra class, this is not surprising. So what we're looking now are the eigenvalues of the operators and their eigenspaces. Okay, so let's see in the case of a compact operator what happened. Okay, what are the properties of these spaces? So number one, let us take some basic properties. Let's take remark before I start some major results of Reed's work. Let T belong to L of X. Okay, so of course we can consider the composition. So we put T to the power 0 to be what? The identity map of X. T1 equals T, and Tn is equal to T composed with T n times. Okay, it's well defined because we are an operator from X into X. Okay, so let us look at, for example, the relationship between n of Tn plus 1 and n of Tn. Okay, so if Tn of X is equal to 0, then T of Tn of X would be also equal to 0. So if X belongs to n of Tn, then X obviously belongs to Tn plus 1, the null space. So this tells us what? That n of Tn is a subspace of n of Tn plus 1. So the first one is 0, the identity map, the null space, the identity map is 0, and they start increasing, okay, as subspaces. What happened now to the range? Okay, so range now. If X, if Y belongs to the range of Tn plus 1, then there exists an X in X such that Y is equal to Tn plus 1 of X. It is very easy to see that Y is the image of T dx under the action of Tn. In other words, so Y belongs to R of Tn. Okay? Which implies that R of Tn plus 1 is included in the range of En. So the range, you start with the first one, which is the range of the identity map, which is entire space X, and you start decreasing. So the null spaces are increasing, and the ranges are decreasing of this power step. So what's happening is, that was some of the results discovered by Bit. In the case of a compact operator, and if you take the A lambdas, because we're looking at the eigenspaces and the eigenvectors, if lambda is not equal to 0, okay, then what happened is that the null spaces, okay, the null spaces, first of all, are finite dimensional. So let's write the theorem. Okay. Let X be a normed vector space. Let A be a compact operator. Then, number one. Before that, let's take lambda not equal to 0. Let lambda not equal to 0. Then, number one. The null space of A lambda n is a finite dimensional space. Oh, interesting. Subspace. 2. R of A lambda n, the range A lambda n, is a closed subspace of X. In other words, the linear operator is a closed subspace of X. And this is true for any n. Okay, then for any n greater than 1, we have. Okay? Keep in mind, there is we cannot expect this result to be true if the operator A is if lambda is not equal to 0. In particular, if you take lambda equals 0, okay, and you take the operator A equals 0, which is obviously compact, then the null space is the entire space X, and if X is infinite dimensional space, you are not going to get conclusion number 1. So we have to be very careful, okay? Proof. Okay. First, let us remark something here, just algebra. Okay. It tells us that if you take A lambda to the power n, in fact, what we're taking is lambda I minus A composed n time. One can show, because A and I commute, that this is lambda to the power n I minus, and you have now sigma of operators where at least you have one A. So the first one that doesn't have A is this one, the one lambda n times I, but the rest you have at least one A. And since you have one A and A is compact from the ideal property we talked about previously, then this will be, every one of them will be a compact operator, and they are all compact, and therefore their sum will be compact. So we can write this minus B sub n, where B sub n is a compact operator. So So here where B sub n is compact. Now this is true for any n. For true, this statement here, for any n greater than 1. So what does it mean? It means that if lambda is not equal to 0, and we know that in this case it's going to be if and only if lambda n is not equal to 0, lambda to the power n, and therefore what we need to do is, it is enough to prove the theorem for n equals 1. If we prove it for n equal 1, then the conclusion will be true for any n. Okay? First, let us prove that n of a lambda is a finite dimensional space. First, so let us prove that n of a lambda is a finite dimensional subspace. Okay. We know that a linear subspace or linear space is finite dimensional if and only if its unit ball, closed unit ball, is compact. So let us prove that the set B1 hat is just to separate between the unit ball of this subspace and the unit ball of the big space X. Okay, that's why I put the hat. So this is X in n of a lambda such that norm of X is less or equal than 1. Okay? So this is exactly n of a lambda intersect the unit ball of the entire space X. Okay? So let us prove that B1 hat is compact. So if I prove that B1 hat is compact, then the subspace will be a finite dimensional space. Let Xn be in B1 hat, then a lambda of Xn equal to 0, which implies a of Xn equals lambda Xn. Okay? But we assume that A is compact. Okay? Therefore, so there exists a subsequence such that A of X phi of n is convergent. Okay, this implies so X phi of n equal 1 over lambda A of X phi of n. So this is where we are using heavily lambda is not equal to 0. Is also convergent. Okay? So which implies that so B1 hat is compact. So keep in mind, now we know it's closed. I mean, so the limit will be there because it's the intersection of two closed sets. So it is closed. It's just once we know that for any sequence in B1 hat, it has a convergent subsequence, that's enough to conclude that the set is compact. Okay. So this implies finally that the space is finite dimensional. Next, let us prove that R of A lambda is closed. The image is closed. This is not true in general. Okay, this is not true in general. But in this case, for continuous, of course, linear operators. But in this case, when A is compact and we take the lambda I minus A, the range is closed. Okay. Now let us prove this. Let Y belongs to R of A lambda bar. Okay. And then there exists xn, okay, in X such that Y is the limit of A lambda of xn okay. So since A is compact, there exists subsequence such that A of this subsequence is convergent. Okay. Let Z equal limit of A of x phi of n when n goes to infinity. Now what do we have? We have A lambda of x phi of n equal lambda x phi of n minus A of x phi of n. So x phi of n is equal to 1 over lambda A lambda of x phi of n plus A of x phi of n. Okay, so now we use the conversions. So we conclude that x phi of n is convergent and limit of x phi of n is equal, when n goes to infinity, to 1 over lambda times y plus z. Okay? So this uses the fact that both the sequence, this one here, is convergent. Okay, so subsequence converges the same limit, and this one is convergent to z.